Hi, my name is Sarah Michelle Hammer, and I'll be talking about the Starlink performance through the Edge router lens. Starlink, as many of you will already know, is a low Earth orbit satellite constellation. It provides internet access globally, and especially in use cases where traditional infrastructure is not as easily accessible. Starlink is one of many operators in the field, but it is by far the largest. It has almost 7,000 satellites in its constellation and more than 4 million users globally. As such, it becomes an interesting object of research. In this research, recent works have established there to be a peculiar 15-second periodic traffic pattern. Specifically, TCP throughput appears to drop significantly in multiples of 15 seconds. Here you can see to the right an example from our measurements. TCP is of course affected by a variety of factors, including latency. Latency in terms of RTT has also shown to follow 15-second patterns, where within one such interval, min RTT is relatively stable, but can change abruptly from one interval to the next, and there are RTT peaks on the boundaries of such intervals. Another factor that can influence TCP throughput is, of course, packet loss, and this has also shown similar 15-second patterns in terms of frequency. Importantly, these 15-second intervals or patterns don't occur unique per dish in terms of when they happen, but rather are globally synchronized. They always occur 12, 27, 42, and 57 seconds past every minute, no matter which dish you look at. This is attributed to a global scheduler and is also considered reconfiguration times or intervals. Knowing that these patterns exist, it was interesting for us to consider where they arise. In any consumer Starlink setup, it usually consists of two proprietary devices. You have the dish and also the router. Generation 2 dishes and those younger than that practically enforce the sort of two device setup because of a proprietary connector. You can't really connect anything else to the dish without substantial effort to modifying the connector. And as such, our understanding of these patterns relies on setups where the router is connected to the dish, used in bypass mode, and there's an Ethernet adapter connecting either further switches or directly the measurement machine. Importantly, in this sort of setup, there's still switching circuitry on the router which is involved, as you can see to the bottom right here. In this way, the router itself becomes part of the black box when we study the Starlink network. The behavior of this isn't quite clear. And importantly, the Generation 1 dishes have a standard RJ45 connector and a power injector, which allows us to directly connect our measurement machine and therefore gain a perspective that is one hop closer to the core Starlink network. With this, we had three main goals in this research. We wanted to understand the Starlink performance from this closer perspective. We wanted to see what the role of the router was in terms of any noticeable patterns, if there is any impact that wasn't visible on non-Starlink equipment, which would of course then inform any future research design. And to sum up, we can say that the router appears to have no noticeable impact on the 15-second throughput drops. How did we get there? In our experimental setup, as mentioned, we had access to a Generation 1 dish, which was mounted on a pole and had no obstructions. And we connected this directly to our measurement machine, which was a Ubuntu machine with a 6.5 kernel and a X550 T2 NIC Intel NIC, sorry. Any sort of NIC offloading or segmentation offloading to the NIC was disabled, and the other side of our performance measurements was a VM in Frankfurt in Azure that was closest to the nearest Starlink point of presence to minimize any terrestrial network connectivity. Both of our measurement machines were synchronized via NTP to the same Stratum 1 server, And these measurements were taken, as mentioned, near Berlin in the summer and spring of 2024, and at different times of day and different weather conditions. So regarding our results, first off, with this more closely connected measurement machine that had no synchronization to any global scheduler or any sort of showed no signs of flow control between the dish and the router, we still saw the characteristic TCP throughput drops on the 15-second intervals. Here to the left, you can see download throughput, and to the right, the upload measurements. And again, gray marks the interval, the 15-second intervals. Knowing that latency was shown in previous works to show these patterns, and now we were directly connected without any sort of possible queuing between the dish and the measurement machine, we took a closer look at latency as well. Here we noticed that, again, similarly to previous work, we saw the same 15-second RTT peaks. We observed this is a 1-hour run with the tool IRTT, which is a UDP-based ping-like tool. And in orange, you can see the RTT peaks. Other important observation here was that the peaks, although they existed, rarely ever crossed the 200 millisecond min RTO value, which would cause a timeout in TCP. We confirmed this with BPF traces, which also saw very rare RTO-triggered retransmissions. This meant that latency itself could not explain the very frequent TCP drops that we observed. Other factors that influence TCP throughput are, of course, reordering and packet loss. And we took a closer look at these as well. To the left, you see socket statistics of a TCP connection, where the retransmission counter in blue clearly shows peaks on exactly the 15-second intervals. Not everyone, but most commonly these peaks occur on 15-second intervals. However, the reordering segment seen counter does not show any similar pattern corresponding to the 15-second intervals. To get an understanding of packet loss, we plotted the difference in sequence numbers from our IRTT runs, and in an ideal world, in a perfect connection, this difference would always be 1 for increasing sequence numbers, which you can also see with a red dotted line. However, if there is loss events occurring, this gap becomes greater than 1, and if there is reordering events, this leads to a negative gap. Here you can see that the positive and greater than 1 gaps of loss clearly outweigh those of reorderings observed. To really understand the role of the router, we had to take a closer look at the link between the router and the dish, which was of course unique to our setup. We looked at the ETH tool rates measured by, to the left you can see our edge router connected to the dish, so basically the rate that is on the link to the dish. And of the corresponding run to the right, you see the arrival rate of ETH tool measurements, the receive rate rather, at our terrestrial node. Clearly, as the data approaches the dish, there's a near constant rate, which is clearly influenced by the traversal through the Starlink network. This is a UDP upload measurement, of course. We also took a look at the queuing in our device, where we artificially limited the bandwidth of this link and saw queuing, and this dissipated as we increased the bandwidth to more closely align to the 1 gigabit link speed that we saw was negotiated, for showing that queuing in this setup and in this set of experiments was not a factor influencing any of these behaviors. This leads us to the following conclusions for Starlink performance through the lens of a device directly connected to the dish. We didn't see any packet drops or queuing at the router itself that could influence this sort of behavior. We didn't see any dish to router link disruptions that would coincide with the 15-second intervals. while reorderings and timeouts due to latency occur, they don't explain the very frequent TCP throughput drops that we observed. Instead, our measurements point to packet loss in the Starlink core network being the most likely cause of TCP throughput drops. While the Starlink proprietary router does not appear to have a significant effect on TCP throughput, it's also notable that any change of the TCP stack on end devices can only fix overreactions to network behavior in the core Starlink network. Thank you for your attention. Have a good day.